course, then this is not instant, but it's okay. While we're here, are you comfortable with people interrupting you?
I am.
And so should I relay the questions from the chat?
Yeah, I'm not seeing them at the moment.
Perfect.
I could do if I was less stupid.
No, it's okay. So everyone, please welcome Sam Lindley, who will give a presentation about the handler calculus. Sam, your turn.
Right. Are you seeing something slightly obscuring my slides at the top? The kind of zoom thing?
No, it is not there.
All right, it's only there on my screen. Fine, good. Good, okay, so yeah, this is a little bit of fun I've been having, well, for a while. A lot of my research I do is on effect handlers, and well, I'll give a short introduction to those for people who are not familiar with them in a minute. But yeah, it's basically a way of generically handling effects in programming languages. But my goal here with this work is to, rather than starting as I normally do with something like a lambda calculus, which has all kinds of features that are useful for programming, and extending that with support for effects and handlers, I want to start with a minimal effect handler calculus and then try and encode all the other standard features you might expect to have in your programming language. So I'll get onto that, but let's just start off with the story about effects and effect handlers. So in an idealized model of programming languages, we might view programs as just being black boxes, taking inputs to outputs, having no kind of interaction with the outside world. But in practice, programs do need to interact with their environment. And in fact, we typically do that via some sort of runtime system or operating system. We have all kinds of different effects, like these ones. And I should actually, yeah, this isn't actually sort of captured on this slide, but it's also useful, as well as having effects that relate to the outside world. Some of these might actually be internal to our programming language. So something like concurrency, we can actually implement within the programming language. And it's just useful to think in terms of interactions, even though we might be implementing that ultimately as using pure functionality. And then, yeah, so the sort of background story here is mainstream systems will just typically, I don't know, languages like C or ML-like languages, they might build in a whole load of effects, but they all have to be, they're typically kind of hardwired into your runtime system. They're not customizable, they're not composable. And if you take a language like JavaScript, it has many different concurrency abstractions, which are all implemented separately, and this is a pain. So effect handlers are an abstraction for implementing all of these kinds of different effects. And there's a rich theory of effect handlers built on the theory of algebraic effects. Crucially, they are composable, customizable, and they allow you to give a user-defined interpretation of effects. And they rely on being able to give direct access to the environment or the context in which you're running. So it's great that Jamie mentioned resumable exceptions in the previous talk. They're very closely related to resumable exceptions. They can be seen as a sort of more expressive form of Lisp-style resumable exceptions. They also, yeah, allow you to do the same kinds of things as monads and limited control operators. In fact, effect handlers are a general structured form of delimited control. The crucial thing that they provide that some of these other things don't so well is the composability and customizability. And there's a lot of interest in industry in these things. They're not just, it's not just a pretty theory. GitHub, for instance, is using this in their semantic library, which gets run on more than 50% of all of their pull requests. And that's used, this is semantic analysis library that relies fundamentally on effect handlers. So, okay, anyway, that's a bit of background. Another way I kind of like to view these things is as little composable user-defined operating systems. So if we take our program here, you can think of being able to decompose that into lots of little mini operating systems, which are the handlers. And this is just indicating how the interfaces, the effect interfaces plug together. But don't worry about really understanding this. This is just an intuition for why this might be useful. It's not really what this talk's going to be about. Yeah, but I am going to give you one example to show how expressive these things are, and to show you how they work. So we can implement cooperative concurrency on top of effect handlers. So you don't have to build it into your programming language. You've got this very expressive feature, and we can implement it. We're going to have a single effectful operation called yield. It just takes a unit argument and returns unit. And the idea is that allows you to yield control from one thread to another. So let's imagine we have two threads, and I'm just going to print some things out and do a yield. And I want to interleave these things together. So at this point, I've written a program in terms of this operation, not giving you any meaning to the operation. It just has a signature. What effect handlers do is they give the semantics to this thing, and you can have different handlers providing different semantics. You can implement different kinds of schedulers, for instance. But here's a basic example. I should say the form of handlers I'm using here is shallow handlers because it makes this example simpler for people who care about such things. But anyway, what's going on? This co-op function here takes a list of threads or resumptions, like the rest of the thread that remains to run. In the case that we have no threads to run, then we just return unit. If we have one thread to run, then we handle that computation. So we handle the resumption. We run it. And so it's a thing of type unit to unit. And this is a generalization of effect handlers, exception handlers, in two ways. One, we have this special clause return, which says what you do if this computation returns a value. And in this case, well, we're just going to return unit here, boring. And then the other one is like an exception clause in a normal exception handler. But as well as yield taking a payload, which is just unit, boring again, it also gets this extra parameter s. And this is the resumption. It's the rest of the current computation. And this is what allows us to resume. But what's interesting about this example is we don't actually invoke s straight away. Instead, we recurse and carry on running this kind of scheduler, but we update the thread to be the new one. So, I mean, okay, what's going on here is utterly boring. It's just going to, every time it yields, it just carry on running. So this is just single threaded, but there is only one thread, so that's not surprising. Here's where the interesting stuff happens. If we have more than one thread, so yeah, this is a list, then we run the first one. I mean, if it finishes, then, well, we just carry on, and with this one's removed from the list. But if we come across a yield, then we get the continuation of the current thread. And what we do is we just pop that on the end of the queue. So that will have the effect of yielding control to another thread. And that's it. So having implemented this thing, we can run co-op with our list, and it does the interleaving as expected. So it's printing these things out and then ultimately returning unit. So yeah, these are really cool. They compose in nice ways. We can implement all kinds of different primitives.
Can I just check that I've understood that code correctly? I think if you take every place in the last definition where s cons rs appears and replace it with rs, that you can drop the second line of the definition, just keep the definitions for empty and r cons rs.
Yeah, you beat me to it.
You're right.
Yeah.
Yeah, that would work. That would simplify it. But this at least gave the idea of in the single threaded case.
Yeah.
Yeah, you're right. No, I should do the simpler version. I started with a version that uses deep handlers, which are a bit different, and moving to the shallow one simplified it. But no, that simplification should work. I'll try that next time I do it. Anyway, on to the actual talk. So this is handler calculus. I'm going to, or these are the types of handler calculus. I'll show you the terms next. So what we're going to have just an empty type and then a type of handlers. So this maps a computation C of type C to a computation of type D, or it handles a C computation as a D computation. What is a computation? It returns a value of type A whilst having some effect E. And then an effect is just a collection of operations and their signatures. And my signatures are n-ary. So they can take n arguments and then return some return value. Okay. And then here
Is 0 the same as the empty type?
Yep, it is.
Okay.
So here's the terms of the language. I'll probably show you this in conjunction with the typing rules when I go through in more detail. But the thing to get from this slide is that we have a separation between value terms and computation terms. Value terms are just variables or handlers. So handlers are kind of first-class things in this calculus. And then computation terms are things that do something. Yeah, and I could have inlined that handler thing up there, but let's look at the typing rules. So I have one judgment for values. Values have value type. Computations have computation type. And most of these rules are completely standard. So for variables, this is the elimination rule for the empty type. And we have let and return. So return injects a value into a computation and you can have any effect you like there. Let is do in Haskell style, but the effects have to be all the same there. And then the things that are to do with handlers are these ones. So operations are fairly straightforward. You have the values you pass to your operation should match up with the types expected of the operation, and then we get back the return type of the operation of B whilst performing the effect E. And this operation is included in this effect. We're allowed to do it. The handle construct is essentially just a form of application. It applies the handler given by this value V to a C computation. So you see it maps a C to a D. And then this is where kind of all the work happens. There's nothing actually surprising here, I don't think, but there's a lot of kind of details. But if you recall, we have this return clause that specifies what you do when you're done. Once you get a value out, we should see that has our final type D here. And then similarly, all of these other clauses have this final type D. And you get parameters passed into the operations with the appropriate type. The technicality is we also get this resumption. And you see the operation goes from AIs to BI. So the thing that the continuation is expecting, that's the thing you're going to insert in your program after you've run the operation, has to be something of type BI. But that itself, this computation doesn't have any effects itself. Okay. Shallow handlers are very similar to this, except you have to have the original computation type here rather than the D. But that's just, I'll show you the semantics and that. So I mean, all that. This stuff is actually fairly standard if you've seen handlers before. And actually my examples are probably going to be more illuminating than the rules. So don't worry too much if you're not getting all the details here. But we only have three main reduction rules, and this one's a standard one for let. If you have a return inside a let, you just do a substitution, but we do the same thing with a handler. If you have a return inside a handler, then you just invoke the return clause doing the substitution. And then again, here's the rule that does all the work. This is the thing that makes the handler deep. You see, well, what are we doing here? We're capturing the context up to the enclosing handler. So that's why I have these pure evaluation contexts. They don't have handle inside here. And then you bind the V's get bound to the parameters that you're expecting in the clause inside the handler, and we need to work out what the resumption is. Well, the resumption is the context. So it's a handler that will just wrap the context around the variable that's returned. But in addition to doing that, it also rewraps the existing handler. And what this means is that you uniformly handle all of your operations in the same way. You don't get to sort of switch to a new way of doing it. Okay, I will give people an opportunity.
Sam, we have a question in chat by one, which is, could we simply replace let construct by an identity operation?
What you can do, and I deliberately have chosen not to, is get rid of let and return altogether, because they can be encoded using handle. But I'm choosing to do it this way because it's kind of convenient for modularity. So yeah, you don't need let. Okay, anyway, the point of my talk is to show that with this little handler calculus, we can encode all kinds of things. Data types in particular. So I'll start off by showing you some sugar. First of all, if I just write, I'll write just the type A with, if there are no effects, then I can omit the brackets here. Convenient to have a notion of funcs. So that's just something that goes from units to C. Quite often we don't care about the value returned. We're just going to use the sort of the operations to encode data types. So we'll be working with funcs over some effect where the return type is actually the empty type. So what you end up having to do there is you have some operation that behaves like an exception. So you never actually return a value. And then, yeah, more syntactic sugar here. If I don't bother writing a return type, then it will be 0. That the handler that is expecting a value of type 0, I'm just going to write as bottom. Yeah, and then the case where we have an exception, i.e. we're handling an operation in such a way that we never invoke the resumption, I write with this syntactic sugar. I just omit the arrow part after this op. Okay, and it's maybe not very surprising that you can encode all these things if you know that computations in this setting denote free monads. And what are free monads? They're given by this fixed point over a functor here, and you can view this. So this is like this defines kind of a tree structure. The A here is the final value you return, and these are the leaves of the tree, and the F defines the nodes of the tree. So if you know what free monads are, and you know about the denotational semantics of this, then this will make sense to you. It won't be that surprising. But now I'll just go through some examples of simple things we can encode. So pure functions, obviously, they're just where we don't have any effects on either side. And then we could do call by value effectful functions where you're going from an A to a computation. And then, well, lambda is just a handler that doesn't handle any operations. It just has a return clause. And then application, well, it's just the handle application in this case. So I should say that this is kind of inspired by stuff we did with the Frank programming language, so with Connor and others, where we already take advantage of this kind of thing, but we have a whole load of other features in Frank as well. I just wanted to isolate some of this out. We can encode unit as a handler that goes from the empty type to the empty type, and then it's just this identity handler.
Sam, so the unit appeared earlier in your sugar without being defined. I was a bit worried about that.
Yeah, sorry,
that
was a mistake. I probably should have defined it first, but yeah.
Okay, right. So 1 is defined in terms of 0, and then the thunk is defined in terms of 1.
Yeah,
that's fine.
Well, and actually, you could write absurd X here as well. That would be another encoding that would also work. That's observationally equivalent. Now we can do pairs. It's sort of not that surprising we can do pairs, given that we've built in the n-ary arguments into the operations. But here's where you see this pattern of we have a thunk with a computation inside it, and the return type of this is 0. We just have an operation called pair that takes 2 types here, and then you implement it in the obvious way. And then you'll see this pattern here. How do we get? So I'm chosen to do projection in this way, where we get both of the components of the pair out at once, and we do that by applying a handler that just does the pattern matching on the 2 components. And then similarly, we sort of for free we get sums. We just define different operations for the different components of the sum. And if you wanted, you can give those different names rather than just having in 1 and in 2. More interestingly, though, and this is really taking advantage of the fact that we have the deep handlers here, which build in a primitive recursion scheme, we can encode inductive types. So here I've done natural numbers. So what's kind of going on here? You see 0, the return type is kind of describing the continuation of the tree structure that is encoding the natural number. So once we got to 0, we just stopped. So we have a 0 here. But with the successor, we have 1. And that means we can have more zeros and successors afterwards. And then you can define, well, you can build up numbers with the obvious encoding. But you can also do a recursor that allows you to implement operations on natural numbers. And this is the 0 case, and this is the successor case. But the crucial thing is that this R here is re-invoking the handler, so it will do the same thing over and over again as you go along the number.
Sorry, I've got a really basic question there, if we could go back. So am I right in thinking this semicolon is part of the definition of a handler in suck V, and then V applied to...
No. Semicolon is just... I don't know whether I remembered to define a syntactic sugar for it, but it's just sequential composition. Do suck. And then...
Oh.
So the point is that computations they're just data structures. They are data structures. And we're taking advantage of that.
So is it defined as a
natural number n is represented by invoke suck n times and then invoke 0.
Yeah. Exactly.
Well, but it looks like I could also do something like invoke suck, invoke 0, invoke suck.
Yeah.
Which natural number is that?
No, you can't. Well, no, you can't, because let's see, can you?
I think you can, but it's 1.
Will never happen.
No, it's
precisely.
As soon as you invoke 0, you have to stop, because 0 is an exception. You see?
Oh, okay. So if I invoke suck, invoke 0, and invoke suck, the answer is it's the same as invoking suck and invoking 0.
Yeah.
I really wonder whether we understand what semicolon is.
It's let x equal suck in. I mean, this one expands into let x equal suck in V applied to unit.
Okay, so semicolon expands in terms of let.
Yeah, did I write that?
There.
No, I didn't. I missed that out there. Sorry, but yeah, it's just the usual expansion in terms of that.
Yeah, and I guess it's an interesting question as to whether you're fussy about the type of the thing left of the semicolon.
Yeah, I am, but that doesn't matter. We can. That's orthogonal. I want to move on because I have like 3 minutes left, and I have a load of material that I'm not going to get through. But we can do natural numbers in the same way. We can also so that gives you inductive types taking advantage of the fact that these are deep handlers. But if you actually have recursive effects, so I'm adding a fixed point construct to effects here, and here I'm giving you an example of why you might want recursive effects. Then you get a different encoding that is a bit richer or a bit more. Well, it allows you to encode negative recursive types, for instance. So this example is like the yield one I had before, except we also have a fork construct that allows us to fork off new threads dynamically. But the point is that needs to have this. You want to be able to fork and yield inside the thunk that you supply to fork as well. So it's useful to have recursive effects. But then we can encode general recursive data types by having roll as an operation, and then unroll just handles it. Okay. Next thing we can do to extend our model is we can add parametric operations, which don't just have inputs and outputs. They can be parametric in the type somehow. So you can think of a sort of polymorphic operation. So a simple example is exceptions. I can use an exception at any type. So I want to say, well, it doesn't have type unit to something. It has type unit to X, where X is any X. And you might think that you could encode polymorphism with these, but you can't. Because really what these things are existentials. So here's the encoding of existentials using this extension with parametric operations. And I suppose that, the point is when you're building these data types, and when you invoke an operation, you're really just packing up an existential. Andre, I don't want to go on too much longer, but I would like to just mention some of the other things.
We can go longer and move Wen's talk a couple of minutes back because her talk is shorter.
Okay, and it's recorded as well, isn't it?
Yes, so we can run it like.
Okay, I'm not going to go on too much longer, but maybe an extra 5 minutes might do me.
Yeah.
Because now my talk completely changes direction, because I became slightly obsessed when I was doing this with this question of encoding existentials and universals. So it's well known that we can encode existentials as universals. So you can encode existentials in system F. And where does that come from? It's basically just, you take the De Morgan dual. If there exists an X such that A, then we know that in classical terms, that's the same as not for all X, not A. And you can kind of expand out the nots as functions into an uninhabited type bottom. Well, like the zero I showed you before. But then the fun trick with system F is you can actually abstract over this bottom thing here and stick an extra universal quantifier around it. And what's really nice about that is it gives you a local encoding of universals as existentials as universals. But in the setting we have at the moment, it's the other way around. We only have existentials. We don't have universal quantifiers. So you can do the similar De Morgan dual trick, but if we try to abstract over the bottom again, it doesn't really work because we're then introducing another universal there. So I was playing around with this and thought, oh, what can I do? And the kind of the observation is, well, we can still use this encoding without abstracting over the bottom. It's just you have to do a completely global transformation. So it's probably not as useful, but it's interesting and fun. And I dug out this work by Fujita from TLCA 2005, who shows how to encode universals into what's called minimal existential logic via a special CPS translation. And it's kind of cool because you can encode the whole of System F into a language that only has these constructs. So we have bottom, we have a restricted form of function. That's what this negation is. It's functions that never return a value. We have products and we have existentials. And that's it. So yeah, you see you have lambda, but this lambda can't ever return a value. We have pairs, elimination for pairs, and existentials and elimination for existentials. And I like this way of, I think Neil had a similar presentation of existentials where you just view them as pairs. So you can see it's the same, syntactically the same kind of construction. You just have a type rather than a term here. Anyway, this is the thing he gave, and I guess I won't go through details. But yeah, it's fun that you can do this. And then the next thing that I'm also not going to give you the details of is we can do a CPS translation of handler calculus into System F, and then we can compose it with this translation. And then that gives you a way of implementing, adding full first-class polymorphism to, or encoding full first-class polymorphism on top of my handler calculus. And yeah, well, is it worth explaining any of this? And this is kind of more or less standard. It's just extended to accommodate these these parametric operations. And I suppose the thing, if you're going to look at anything, you'd look at was the translation on types. So, well, the empty type go to the empty type, and then handlers turn into a pair of a continuation and this dispatcher thing here, which models the handler. And if we look at these things, the R here is the return type, and you can see that that itself is a computation. So this allows you to compose these things together. And that's the definition on terms and on judgments. But I'm going to stop with a couple of questions. I mean, I'm not sure that any of that last stuff is actually necessarily useful. Probably the thing to do would be to just add polymorphism to the handler calculus in practice, but it was just a fun exercise to think about it. Things get more interesting when you start thinking about effect polymorphism, which I haven't considered here. And that's crucial in practice. I would have liked to have had a compositional translation of universals in handler calculus straight into a minimal parametric handler calculus rather than minimal existential logic I gave. But I didn't work out the details of that. Anyway, I will stop now, and you can, I guess, ask me questions in Gather.
Great, thank you. So we're going on Gather for a short break. I just realized that it might not be a good idea to push back Wen's talk. So we're going to see each other in 10 minutes and then have a slightly longer break. All right, see you in a bit.